Okay, so today's lesson is going to be about deriving formal trig identities, and this lesson is going to come in a few different parts. We know a little bit about this already. We know some formal trig identities like the Pythagorean identity. You might think back and remember your even and odd identities, where sine is odd and cosine is even. You might also think back to your cofunction identities, how sine of one angle is equal to cosine of pi over 2 or 90 degrees minus another angle. So we're going to take those identities and come up with a set of new ones. And the new ones are called an angle sum identity, an angle difference identity. Now there will be angle sum and difference identities for sine, for cosine, and for tangent. And then also we'll learn the double angle identities. Okay, so when you put all of these together collectively, these are often referred to as your formal trig identities. So let's put on bow tie and let's get started. This whole thing is going to start with a derivation of what is called the cosine difference identity. So cosine difference identity is essentially what we're trying to do is we're trying to come up with a new and a clever way to think about the cosine of the difference of two angles. Now, we know if we have a cosine of alpha minus beta, just so in case that's not clear, this first little fishy thing, that's an alpha. I'm thinking about that as my first angle, and the second fancy b, that is the Greek letter beta. So alpha minus beta is the difference of two known angles. So we know we can't just subtract the cosines of those two angles, but the question is, what can we do? Is there a way we could rewrite cosine of alpha minus beta? So this proof, this derivation is a little bit long, but you should know that the other ones will sort of fall right out from this one, so it's pretty important. So to come up with a way to write cosine of alpha minus beta, I'm going to start with, of all things, a unit circle. So here's a unit circle, and on this unit circle, I'm going to draw in red here a little angle alpha. I'll put it in quadrant 2, but where I put it is kind of arbitrary. So here's my angle alpha, and rather than labeling it like that, I'm just going to mark this coordinate here where the terminal side meets the circle, and of course that would be the coordinate cosine alpha, sine alpha. Okay, and now I'm going to draw another angle, a little smaller than the first one. It doesn't need to be smaller, but that's how I'll draw it, and I'll mark that beta. So that's my second angle. Feel free to use A's and B's if you don't like drawing the alphas and betas. And to mark beta, I will simply mark this coordinate up here as cosine of beta, comma, sine of beta. Okay, now in that picture, what I'm going to start to focus on is rather than the angle alpha or the angle beta, I'm going to look at this angle that I created in between the two. That angle in between the two would be the angle alpha minus beta. So I need to come up with a good way to visualize alpha minus beta. So what I'll do is I'll redraw this picture. I'll redraw my unit circle right over here. And that wasn't very straight. And in this second picture, what I'll do is I'll take that green angle, alpha minus beta, and I'll put it in standard position. So standard position means you put the initial side on the positive x-axis there, so it meets at 1, 0. So this is describing the angle alpha minus beta, but to indicate that, I will simply label this coordinate up here where the side terminates, and that would be cosine of alpha minus beta, comma, sine of alpha minus beta. Okay, now what can I do from here? The idea from here is that the two pictures have a common difference, a common distance in them. The distance between the terminal sides in the first picture and the distance between the terminal sides in the second picture are equivalent. So if I just call those D1 and D2, I can start this derivation by saying that I know, or we know, that d1 equals d2. So this is now going to fall out from here using the distance formula proof. So in case you forget, we're going to use the distance formula where you just extend the Pythagorean theorem, where you subtract the x-coordinates and square, and then subtract the y-coordinates and square. Okay, so I'll do that for the picture on the left, and I'll do that for the picture on the right. When I do it on the left here, I get a big square root. I'll get cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared. And on the right, my x-coordinate difference would be cosine of alpha minus beta minus 1 squared plus sine of alpha minus beta minus 0 squared. Okay, so you made a big mess on the page. And we've seen this before with identities sometimes. They get kind of messy, and then you just have to do some operations to clean them up. So the first thing that I'll do is I will square both sides. So in squaring both sides, I will just get rid of these square roots, those ugly square roots. And then the next thing that I'll do, of course, is I'll expand these binomials that I've created here. Cosine alpha minus cosine beta, and then the sine alpha minus sine beta, and then the cosine alpha minus beta minus 1. All those binomials are being squared. Of course, I'll point out the last one here technically isn't a binomial because it's sine alpha minus beta minus 0. So I'm going to write those all out. And I'll try to keep it as organized as I can. It'll become a real mess, and then it'll start to clean up. So as I write it out, it becomes cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. That was the yellow part. And then next I will multiply out the second binomial. It'll be sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. That is the red part. And then on the other side of the equal sign, I'll have a cosine squared alpha minus beta minus 2 cosine, and I'll just get this thing out of the way here. Nope. Go away. There it is. 2 cosine alpha minus beta plus 1. That is the blue part. And the green part, I'll just squeeze in right here, will be plus sine squared alpha minus beta. Okay, great. In the next step, what I'm going to do is I'm going to look at this big mess that I've created and see if there's anything I can simplify. So just take a look at it. Do you see anything in there that could be written much more simply? One of the nice things about working with these formal identities is you get a chance to think back over things you've done before. So one thing you might recognize here is on the left-hand side of the equation, you had a cosine squared alpha and a sine squared alpha, and those two are equal to 1. And you also had a cosine squared beta and a sine squared beta, and those two are also equal to 1. So as I rewrite the left-hand side of the equation, I can actually write it much more simply, just as 1 plus 1 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. And on the other side of the equation, I'll notice that I also had a cosine squared plus a sine squared. And then I had another 1 here that I got when I expanded the blue binomial there. So 1 and 1 again is 2, and it's 2 minus 2 cosine of alpha minus beta. Okay, so I'll remind you that what we were trying to do here all along was come up with a nice way to rewrite cosine of alpha minus beta. And you can see now that we're actually very, very close to that. What I'll do is I will subtract 2 from both sides of the equation. So I'll just cancel out these 2's here. And then I'll factor out a negative 2 on the left-hand side of the equation. I factor out that negative 2, I get cosine alpha, cosine beta, plus sine alpha, sine beta. And on the right-hand side, I have negative 2 times cosine of alpha minus beta. Now what I'll do is I'll multiply both sides of the equation by a minus 1/2, and I'm done. I'll write the cosine alpha minus beta, which was on the right, over here on the left instead. And what remains is a nice way to rewrite cosine's difference using the angles alpha and beta individually. So this thing right here is referred to as cosine's difference identity. Okay, so the natural thing is, what was all that work for? Are all these going to be that difficult? The answer to that is thankfully no. Once you know cosine's difference identity, and that was a good amount of work, it's quite easy to work out a bunch of other identities. The natural question might be, how could I then figure out cosine's sum? What about cosine's sum? What if I add the angles instead? Let's show why you don't have to start all the way back in the beginning. If I want to know about the cosine of the sum of two angles now, alpha plus beta, what I can do is actually very, very clever. What you can do is you can say, oh, alpha plus beta is really the same as alpha minus a negative beta. Alpha minus a negative beta. So what I'm doing here now is I'm thinking about my first angle as alpha and my second angle as minus beta, and I'm just following the prescription that I came up with for cosine's difference. See, cosine's difference is going to work anytime we have two angles subtracted. No one said that those two angles had to both be positive, so I could think about them as being cosine of alpha minus a negative beta. And let's just see how that's going to work out. So following the prescription that we came up with up here for cosine's difference, I'm going to get cosine of the first angle times cosine of the second angle, which is minus beta, plus sine of the first angle times sine of the second angle. And now, what I'm faced with is I see a cosine minus theta and a sine of minus beta, and I think automatically that maybe I should use my even and odd properties, and that'll work out just nice. So cosine of alpha times cosine of beta, I remember that cosine's even, plus sine of alpha times sine of, sine is going to be odd. So what I'll do is I'll factor out that minus sign and write it as a positive beta. And that tells me that cosine's sum looks very, very similar to cosine's difference. It's cosine alpha, cosine beta, minus sine alpha, sine beta. And that is cosine sum identity. Okay, so the question now is, what is all this good for? Why do we need these sum and difference identities? How could they potentially help us? I think that's a pretty natural question, and it's one I think we're ready to answer before we get into the other identities that we'd like to figure out today. So, how might this help us? How might this help? Well, there's a lot of ways that it can help actually, but just to kind of get started, here's a value, cosine of 15 degrees, that I couldn't work out before. I might need a calculator for it. It wasn't a known value on the unit circle. But now I could think about 15 degrees as a difference between two angles. I could think about it as the difference between 45 and 30, which are known values on the unit circle. And then I could follow the prescription for cosine's difference identity, cosine 45, cosine 30, plus sine 45, sine of 30, where I just think about 45 as the first angle and 30 as the second. And of course, that would be equal to root 2 over 2 times root 3 over 2 plus root 2 over 2 times 1/2. And simplifying, that would give me root 6 over 4 plus root 2 over 4, or root 6 plus root 2 all over 4. I've got a nice way to write cosine of 15 degrees now. Yeah, that's wonderful. What else? If I wanted to show how you could use cosine sum identity, we could work out maybe cosine of 75 degrees. And you could see that that could be written as cosine of 45 plus 30. That's a nice way to get 75. And if I follow the prescription from cosine sum, if it wasn't clear already, I just thought I should point out kind of an interesting feature that cosine's difference has a plus and cosine sum has a minus. It's a little backwards of the way you would wish it would be, but that's how it is. So that means cosine of 45 plus 30 is equal to cosine of 45, cosine of 30, minus sine of 45, sine of 30. And of course, this will follow exactly like the problem above with the noted difference of a minus sign between the terms. So we get root 6 minus root 2 over 4. And this is a good place to pause and to think about what's coming next. What's coming next is what about sine? What about sine? Well, just to give you a little hint before you watch the next video, we actually know a lot about how to do sine because we know, for example, that cosine of 15 degrees is equal to sine of 75 degrees because of our co-function identities. And we know that, likewise, cosine of 75 is equal to sine of 15 for the same reason. And those co-function identities are going to be the key to deriving sine sum and sine's difference. So if you'd like, before you watch the next video, see if you can play around and come up with a nice way to write sine of alpha minus beta and sine of alpha plus beta. Okay, see you at the next video.